Well, howdy, folks. Well, this should be our last installment of Lectures from the Living Room. I have mixed feelings about seeing it come to an end. I'm just getting used to this. But anyway, I just wanted to wrap this up with a little discussion about organic chemistry. And they reserve this at the end of the chapter. I mean, it's really, like I said, for those of you who are destined to take organic chemistry in the fall with Dr. Halverson, or where you might transfer to. But anyway, chemistry of carbon fills up 2 whole semesters. Carbon being kind of unique in that it can form these long chains. Catenation, that's the word for it. Its ability to bond to itself and form these long chains. And it can form branch chains, cyclic chains that are ring structures, and its ability to double bond and triple bond to itself. And it gives rise to just a whole host of compounds. So anyway, let's start at the simple ones, the simple hydrocarbons. Okay, organic chemistry is going to start off right here with the simple hydrocarbons. These are compounds of just carbon and hydrogen, and they're basically grouped into 3 categories. Actually, I'll add kind of a subtle 4th category here at the end, but they're called the alkanes, the alkenes, and the alkynes. Now, the alkanes, sometimes referred to as the paraffins, like paraffin wax is an alkane. These are compounds of carbon that have only carbon-carbon single bonds. And these are called saturated hydrocarbons because when a carbon is single bonded, it's holding as many hydrogens as it possibly can. When they refer to saturation, they mean saturated with hydrogens. The alkenes, on the other hand, are unsaturated. Whenever there's a double bond in a compound, that means that it only has room for 2 other bonds on there, and it's not holding as many hydrogens as it possibly could, like an alkane might, where again you could have 4 bonds on each carbon. Remember the rule of 8, so everybody gets 4 bonds. All right, so the double bonded and triple bonded hydrocarbons are referred to as unsaturated. All right, you hear that term when you talk about fats, saturated fats versus unsaturated. That's what they're talking about. The unsaturated ones have double bonds. And the polyunsaturated fats have lots of double bonds, and these are good for you. All right, so anyway, these 3 basic hydrocarbons are referred to as the aliphatic hydrocarbons. I'm going to put that category up here in a second. Now, the alkenes, just a couple anecdotal things there. The alkenes are sometimes referred to as the olefins. And if you hear an organic chemist say that something is olefinic, it just simply means that it has a double bond in it somewhere. Again, the alkanes, their common name is the paraffins. The alkynes that have carbon-carbon triple bonds in them, at least 1 or more, are referred to as the acetylenes. Now, this is because the simplest hydrocarbon that has a triple bond in it is this compound. It has 1 hydrogen on each carbon. Because, again, the rule of 8 dictates that each carbon has 4 bonds, and so consequently the triple bond takes up 3 of them and leaves just room for 1 hydrogen. This is the compound acetylene. And so consequently, compounds that contain triple bonds are sometimes referred to as the acetylenes. All right, well, let me show you that subtle 4th category that I mentioned. Okay, this 4th category of hydrocarbons are the aromatic hydrocarbons. Now, these compounds are based on the compound benzene. They contain at least 1 benzene ring to be classified as aromatic. And benzene has the formula C6H6. It's a cyclic structure, and I don't know if you recall this, but back in Chem 130, when we first introduced Lewis structures, we talked about resonance, when a double bond could be drawn in more than 1 equivalent position. Well, it turns out to make C6H6 work, there has to be a double bond every other carbon-carbon bond. But that double bond could just as easily have been drawn 1 click over. So benzene exhibits resonance. As a matter of fact, you'll see its abbreviation like this, just a hexagon with double bonds at alternating positions. Or sometimes you'll see it just drawn like this with a circle inside to indicate the resonance of those double bonds, because they could be drawn at either one of the 2 positions that are there. But again, those electrons never sit still. So benzene has some kind of unique properties because of these delocalized, like a donut of electrons above and below this hexagon of carbon atoms. All right, well, it turns out that there's a whole class of aromatic compounds where we put attachments on the aromatic compounds, or I'm sorry, on that aromatic ring on a benzene. All right, well, I want to go back and I want to just show you really quickly how they name some of these simple hydrocarbons. Okay, I always appreciate it. I kind of like the way they figured out this system for naming organic compounds because they all look very similar. And so you had to have a systematic method for naming them. And the International Union of Pure and Applied Chemistry came up with this system. So they call it the Iupac method, Iupac. All right, well, essentially they assigned a prefix to stand for the number of carbons that appear in any molecule, for instance, or any little branch of a molecule. For instance, the number of carbons, if there's just one, it uses the prefix meth. For instance, like methane. You'll notice that the alkanes all end in ane. This is the other thing I like about the Iupac system, is when you see the end of the name, that suffix will indicate what class of compounds it generally belongs to. Alcohols all end in ol. Ethanol, methanol, propanol. Aldehydes, ethanol, propanol, they all end in al. So again, there's nice little subtleties in the Iupac system that make it simple to learn. All right, well, for instance, methane, CH4. Easy enough Lewis structure. It's only got 8 electrons. And it turns out that sure enough, as you begin to chain these carbon atoms together, for instance, 2 carbons is ethane. Well, it looks like this. 2 carbons bonded together. All the other spots, remember each carbon has 4 spots. So the other 3 spots would be filled with hydrogens. So the formula for ethane with 2 carbons is C2H6. So the condensed formula would look like that. The more structural formula would look like this, the Lewis structure. Now they even kind of do something in between, writing just the condensed molecular formula and the structural formula. They'll condense each carbon center and call this like CH3 linked to a CH3. Now you can see that that might be at least a little bit more portable, or at least easier to do than just drawing all the hydrogens all splayed out like that. But again, you'll see the formula for ethane written one of these 3 ways, just as a molecular formula or as a structural formula or as what they call a condensed structural formula. All right, well, let me continue on with 3 carbons. Propane, they use the prefix prop. So this applies across the spectrum of organic compounds. Anytime there's 3 carbons, it's going to have the prefix prop in it. So for instance, propane. Well, propane is an alkane, meaning it's just carbon-carbon single bonds. And if it starts with prop, that means there's 3 of them. All right, and again, the hydrogens would be bonded in such a way to meet the rule of 8 so that everybody has 4 bonds. Well, that would make this one on the end a CH3, this one in the middle a CH2, and this one on the other end a CH3. So this would be sort of the full structural formula if I put all the hydrogens on. But after a time, the organic chemists, obviously, this gets a little tedious, and so this, again, kind of gives the essence of the 3-carbon chain, but it doesn't just show all the hydrogen bonds. All right, so let's continue on, but let's use this condensed molecular, or this condensed structural formulas. Now, if we go to 4 carbons, you can see what's going to happen here. All we do is add another CH2 in the middle of the chain. This would be butane, C4H10. All right, so 5 carbons is going to be pentane. From then on, I mean, at least it was understandable that they were hard-pressed to come up with nice prefixes, but they finally realized that when they got to 5, the 6th one could be just hex, hexane, 7 would be heptane, 8 would be octane, Heard that word before. Then 9 is nonane. I'm sorry, I started naming alkanes. I just want the prefix here. Octane, nonane. 10, they use DEC as the prefix. So decane would be a 10 carbon chain. All right, so that's how the alkanes are named. Now here's what gets interesting. Alkanes can have little branches that grow off of them. So let me just show you that real quick. Okay, these organic chemists, they got a name for everything. They refer to any branches that occur on like a parent chain. So I've got this parent chain of carbon atoms. And again, they would have hydrogens attached to them to fill out the rule of 8. So for instance, these ones in the middle would have 2 hydrogens on them, but anything on the end would have 3. All right, well, if there's a branch that takes up one of the bonds, say on this carbon atom, they refer to a branch as an alkyl group. That's spelled A-L-K-Y-L. It's pronounced A-L-K-E-E-L, alkyl. All right, so an alkyl attachment, an alkyl group, that's what they refer to it as, is named based on how many carbons are in the branch. But its name now ends in YL after alkyl. All right, well, a 1-carbon branch, which I could draw any 2 different ways. For instance, I could draw it full structural way with 1 carbon branched off of, my parent chain and show all the hydrogens. Or I could condense that and just make it a little CH3 dangling off of the parent chain. Well, it's a 1 carbon, so they use the METH prefix, but they end it with YL because it's an alkyl group. It's attached to a larger parent chain. So they would call this a methyl group. Well, imagine what they would do if there were 2 carbons in a row dangling off of a branch, say a CH2 and a CH3. Well, they refer to that as an ethyl group attached. So this 1 carbon one is a methyl. This is ethyl. If I had 3, CH2, CH2, CH3, it's called a propyl. Again, based on 3 carbons. Here's an interesting one. If I put 3 carbons, but I do it like this, where it's in like a little T, so CH3, CH3, this carbon gets 1 hydrogen. That's still a 3-carbon branch, but instead of grabbing it by the end carbon, we grabbed it by the middle carbon and attached it. They call this an isopropyl. You've heard that term, I'm sure, in reference to isopropyl alcohol. And later when we get to alcohols, I'll show you how that applies. But again, these are the typical branches that you can hang from a hydrocarbon. Now here's where the game gets fun. Okay, to complete the picture on how they name these compounds, here's a compound with a little branch on it, a methyl branch that's attached to it, a methyl group. But the parent chain is actually right here. It's 6 carbons long. So that's 1, 2, 3, 4, 5, 6. That's hexane. So the name of this compound is based on the parent chain, hexane. But then out in front they list all the branches. Well, in our case we have only 1 branch. We have a methyl group. So this is called methylhexane. But that doesn't tell us where the methyl group is on the parent chain. So you figure, well, you got to have an addressing system. So they number the chain. Well, which carbon atom is it hanging from? This is number 1, number 2, it's on the number 3. This is 3-methylhexane because the methyl group now hangs from the 3rd carbon. Well, here's the thing, there's subtle rules because they make you number from the end of the chain closest to the branch. Because if somebody numbered it from that end, they might call it 4-methylhexane if they were standing on the other side of the molecule. So everybody has to follow the same rules. You got to number from the closest end. And what if there are 2 methyl groups? Say there's another methyl group here. Well, let's call that dimethyl. But now we have a responsibility. We got to say where both of the methyl groups are. We can't just say 3-dimethyl. It's got to be 3,3-dimethyl hexane, because we have to give an address to each of the methyl groups. For instance, what if I did this? Put the methyl group on this carbon. Well, now, regardless of which end you number from, this is a 3,4 dimethyl. Again, it gave the address of both of the methyl groups. All right, well, then it gets even more interesting. What if there are different kinds of branches, like methyl groups and ethyl groups? Well, then we alphabetize them. So the ethyls always come before the methyls. Each branch gets its own number, so you can see that the names could get quite elaborate if you've got a pretty good sized hydrocarbon and a lot of little branches on it. All right, well, now that you've seen, sort of at least got your feet wet on how we name these simple alkanes, let me show you the alkenes real fast. Okay, here we go, naming alkenes. Now, the only difference is that they end in ene. So you've heard words like kerosene, ends in ene, likely a mixture of alkenes. Well, it turns out that with a double bond in there, that's what qualifies it as an alkene. In this case, it's based on a 5-carbon chain. So this is referred to as pentene. Did I count right? 5? Yeah, pentene. Now the thing is, though, that double bond could just as easily have been here, or maybe, well, there it would still be the second one from this end. Here it's the second one from this end. So if we just flipped it over, we can't do mirror images, but it could have been here or here. Well, that means that we have to be more specific. We can't just say pentene. We're going to have to say where the double bond is. So they number the bond positions. And again, you would number from the end of the chain closest to where the double bond is. So in this case, this is called 2-pentene, meaning the second bond position has that double bond in it. Now, once you've established it's a pentene and you've numbered from the end closest to the double bond, regardless of where there might be any branches, you've already established that this is the end that you're numbering from. So for instance, what if I put a methyl group down here south of the double bond? Well, I've already planted my foot that this is the second bond position, meaning this is the number 2 carbon. So this is 1, 2, 3, 4 methyl. Sorry, I squished that in there pretty good. 4-methyl 2-pentene. So you can see they've got a definite method to their madness, that looking at how you could put hydrocarbons together with just very few atoms, you can come up with an unbelievable number of structures. And to have a systematic way to describe to somebody in a name how they could recreate that structure was a pretty daunting task, I would suppose. And so anyway, they came up with the most foolproof system, for naming organic compounds. And as you play the game, I think you'll earn the appreciation and earn an appreciation for it. Well, anyway, let me just show you very quickly an alkyne. Okay, well, the alkynes, I didn't even put that up here. Commonly referred to as the acetylenes because the most common alkyne is the one with just 2 carbons. Now, technically, its name is ethyne because it's 2 carbons, ETH prefix, whenever there's 2 carbons. And it's got to end in YNE because of the triple bond. But they commonly refer to this as acetylene, which is confusing because that makes it look like an alkene, but it's not. It's an alkyne. So anyway, naming system, same. If I have like a 5-carbon alkyne, it would be based on pent, meaning 5 carbons, pentyne, and I'd have to indicate where the triple bond is, so this would be 2-pentyne because the second bond position. And again, you number from the end closest to the triple bond. Okay, well, I just want to show you, now that you've seen kind of a rough sketch of how they name these and how they name branched hydrocarbons, let me show you a couple of the reactions of the alkanes and alkenes. All right, well, one of the common reactions of the alkanes is halogenation, to add a halogen to it, like a chlorine or a bromine or an iodine or a fluorine. And it turns out not too difficult a reaction. If we it takes a little bit of ultraviolet light, as a matter of fact, to get this reaction started. But if we took some ethane, for instance, just ethane gas, And by the way, I didn't mention this before, but the lighter hydrocarbons, all the way up to propane, are usually gases at atmospheric pressure. And even butane has such a high vapor pressure that to keep it as a liquid, you really have to compress it, like in a lighter. So again, the first four gases at standard conditions. When you get to pentane, the molecule is large enough that its London forces actually make it a liquid at room temperature and atmospheric pressure. So, but it'll evaporate pretty fast, pentane will. And hexane gets a little heavier. By the time you get to, decane, it's getting a little thicker, a little more viscous. And as you add carbons to that and make alkanes that are longer and longer, eventually they become very oily looking. And then they become a waxy solid. By the time you get to about 22, 24 carbons, you've made paraffin wax, which is a nice hard hydrocarbon. All right, well, I'm going to use ethane gas in this reaction and chlorine. Well, it turns out one of the chlorine atoms will snatch one of the hydrogens off of there to make an HCl, and the chlorine will take its place. They call this chloroethane. We're so clever. If it was a fluorine, it would be fluoroethane. If the chain is long and you have to indicate, well, where is the chlorine attached? Guess what? They use a number. And if there's more than one halogen attached, they alphabetize them. But each one gets its own number address. So you could have things like, 2-bromo-3-chlorohexane. Well, there's a bromine on the second carbon and a chlorine on the third carbon, and it's a 6-carbon parent chain. So you're getting an idea what the code is like here. All right, well, one other kind of notable reaction of the alkanes is combustion. All right, let me put it up on the board. All right, well, we've been looking at combustion reactions since the beginning. Since we first started looking at balancing equations, we use these to practice on. But again, it's just the reaction with oxygen, and all the hydrocarbons are notoriously flammable. They'll burn because carbon dioxide is such a stable molecule, and so is water. And those are the two compounds you're going to produce. So it's a downhill roll in terms of enthalpy and entropy. So consequently, it's got everything going for it. Big negative Gibbs free energy. All right, so you're always going to make CO2 and water out of this. Very easy to balance these. So that's it, really. The two notable reactions that they talk about in your text, although the alkanes do undergo lots of other reactions, is the halogenation reaction and this combustion reaction. Now, let me show you the alkenes, because things get a little bit more interesting there. I'm not going to do reactions of the alkynes because you don't find any of these in human physiology. I mean, there's some notable reactions with them, but nothing that would lend itself to human physiology. And so for those of you who are studying in the life sciences, I'm just not going to take the time to look at any of their reactions. But let's look for a second at the alkenes. Okay, I'm going to reach way back into Chem 130 when we talked about hybridization. Whenever you got a double bond between two carbon atoms, each of the carbons is sp2 hybridized. That's all going to come back to you when you get into organic. Now, it turns out that it kind of takes a trigonal planar arrangement there, but the double bonds that occur in hydrocarbons, and I'm not going to show the rest of the parent chain, but it turns out this is a very active site. Oxygen can attack double bonds there. This is why fats, for instance, that have lots of double bonds in them will go rancid after a while, because oxygen, as it mixes in with the oil, attacks at the double bond and breaks this apart and puts a double bonded O on each of the two carbon atoms and essentially makes little compounds called aldehydes out of them. The aldehydes are what make human sweat smell the way it does. And so this is why rancid oil has kind of a weird human sweat type smell to it, because of the fact that it's oxidizing into these aldehydes. All right, well, anyway, the double bonds turned out to be a very active site, a place that the molecule can be attacked. Because if we could open that gate, that would provide two new bonding sites, one on each carbon. So all we need is a little delta G push in that direction. And so consequently, addition reactions are what happen. Well, let me put that up here. Well, an addition reaction can happen this way. A hydrogen molecule, H2, can be smacked into that double bond. I talked about this when we talked about the hydrogenation chambers that they have up at the USDA lab that are pointed out there at I-74. All right, well, anyway, the hydrogen can actually be banged into that double bond and cause it to open up. And that saturates the bond. It makes an alkene into an alkane, meaning now there's no double bond, now it's a single bond. So they refer to that as a hydrogenation reaction. Again, we're so clever, we added hydrogen, hydrogenation. All right, well, we can also halogenate the double bond. For instance, if we take a chlorine molecule, Cl2, I'm leaving off all the lone pairs there, and smack it into the double bond, sure enough, you can make a dichloroalkane out of it, meaning the double bond is gone. But yeah, suddenly we got chlorines on both of the carbons that are there. Here's what's interesting, is you can actually smack a water molecule into that double bond, and I'm going to draw it as HOH. Because here's what happens. A hydrogen adds to one of the carbons, and an OH adds to the other carbon. Well, an OH attached to a hydrocarbon makes that compound an alcohol. So it turns out, sure enough, you can convert an alkene with a double bond into an alcohol with a pretty simple little addition reaction here, and bust open the double bond and put what's called a hydroxyl group. Remember, we called an OH when they were ionic, we called them hydroxide. Well, when they're attached to a hydrocarbon, they're attached covalently, not ionically. And since they're an attachment, like an alkyl group that ended in YL, like a methyl, well, we end those in a YL, so it's called a hydroxyl group that's attached. And hydroxyl groups are typical of alcohols. All right, well, now I didn't look at all of the reactions. Obviously, there are a lot that the alkenes can undergo. They have a very interesting chemistry. But I want to show you a couple things about aromatics before we move on. Well, the aromatic compounds honestly deserve an entire semester's course all on their own. There's so much interesting chemistry that goes on with that benzene ring and all of those double bonds that are there where you can put attachments on. And you can put multiple attachments around the ring. For instance, if you put a methyl group on a benzene ring, it's called toluene. If you put two methyl groups, like another one over here, it's called xylene, but you could have it different ways. You could put the methyl group here, here, or here. Well, so there are xylenes, plural, that have two methyl groups. And again, just all these different attachments to make all of these different compounds, all based on benzene, and consequently collectively referred to then as the aromatic organic compounds. This one, aniline, is used in a lot of different fabric dyes, hair dyes, wood stains. A very good solvent. It takes to organic material very well. But again, most of these compounds, these aromatic compounds, not good for us. Benzene is a known carcinogen. It's probably the most used solvent in the United States because it's used to manufacture all of this different array of aromatic compounds. And consequently, there's always, a little environmental issue going on with benzene. And consequently, most of its cousins here are not necessarily good for you. The aniline that occurs in dark women's hair dye or men's hair dye is now linked to bladder cancer, that it can soak through the scalp. Again, not great to come in contact with this one. This one, phenol. This was one of the very first antiseptics we ever came up with. Joseph Lister, the guy, Listerine guy, I mean, he made weak solutions of this and would spray the surgical area in their hospital. He was a surgeon, and all of his instruments and post-operative infections just went to practically nothing. Up until that time, with hardly any antiseptic used in the operating arena, a lot of times an operation was successful, but the patient died from the post-operative infections. Well, the use of weak solutions of phenol kind of turned the tide there on post-operative infections. And as a matter of fact, we still use, you've probably smelled this or tasted it because it's the main ingredient in most throat lozenges, like Sucrets. That real medicine-y kind of smell from Sucrets, that's that compound phenol. Well, anyway, I just picked like three kind of interesting ones. But anyway, let's go on. I want to show you some other functional groups, other classes of organic compounds. I forgot to mention one other really interesting aspect of naming the hydrocarbons is this idea of structural isomers. If you look at the molecular formula, C5H12, 5 carbons. Now, the simplest hydrocarbon you could write with that formula is this: 5 carbons in a row, CH3s on the end, CH2s in the middle. Sure enough, you count up the hydrogens, there's 12 of them. Right? Yeah, 12 of them. But there's other ways you could draw that structure. If you just saw that, C5H12, what's to keep you from doing this? 4 carbons in a row and one dangling off, a little branch. This is 2-methyl-butane. It's not even a pentane, but it's got that same molecular formula. Well, in organic chemistry, they refer to this as isomers, compounds with the same molecular formula but different structures. All right, so just because you know the molecular formula doesn't mean you know anything about that. You really need to draw out the structure to know what compound it is. For instance, I could draw a C5H12 like this, with 1 carbon in the middle and branches all around. That's actually called 2,2-dimethylpropane. I'll let you figure that one out. All right, but you can see structural isomers could get interesting. The more carbons you have, the more possibilities you have. So you could come up with a lot of different structures if we get up to like C8, C9. All right, well, anyway, you get the idea. Now there's one other kind of isomerism, but I'm gonna have to go get my model kit to show you this one. So hold on just a second. Okay, the other type of isomerism that shows up in organic chemistry, and it really strains your ability to visualize 3D, is optical isomerism. And again, this happens with carbon atoms because they can form these tetrahedrons. Now, when you have a molecule where a carbon is attached to 4 different things, doesn't matter what the 4 things are if they're different from one another, then I could come up with a molecule. Oh, drop my chalk there. And let's see, let's put the white ones up, green ones in front. All right, now if you look at these 2 molecules, white up, I said that and didn't do it, white up, green in front. These are identical molecules. Notice that the yellow is to my right, the red is to my left, the green is down, the white is toward you. Those are identical. They're superimposable upon one another. However, if I change just 2 legs, doesn't matter which one I do, let me just change 2 on this one. Okay, now again, I'll put the white up, green in front. Now look at them. They're mirror images of one another. Okay, oh, let me get the green towards you, like that. Notice that now they're not superimposable over each other. That the red and yellow ones look like they're on the wrong side. So there's a right-handed and a left-handed version. All right, well, it turns out that this happens with very important biochemical molecules, for instance, like amino acids. Here's one of the 20 essential amino acids, alanine. Looks like this. All the amino acids look like this. The only thing that changes is this little side chain right here. When you get to biochemistry, this is one of the big chapters, is on amino acids and how they link together to make proteins. All right, well, it turns out that the only thing that changes is this little side chain. The rest of the structure is always the same. Well, this carbon in the middle, notice, has 4 different things attached to it. So sure enough, there's right-handed amino acids and left-handed amino acids. And we only use one of the 2 forms in human physiology. The other form is just not used. All right, because again, the shape of the molecule dictates its function, and so consequently, maybe in an alternate universe, they may use the other handedness of the amino acids, but we don't. All right, so anyway, now 2 types of isomerism we looked at, the structural ones and the optical, sometimes called stereoisomers. So anyway, you'll see that this adds an extra little flavor then to the organic chemistry that you're going to study. All right, well, I want to show you some other functional groups, some other sort of attachments that make molecules into something else. Okay, well, the first functional group that they introduce you to in organic chemistry is called the hydroxyl group. I mentioned it before, the OH group when it's attached, and it's typical of an alcohol. I mean, that's what That's the functional group that makes a compound into an alcohol. Now, I've abbreviated the parent chain as just the symbol R. This is the symbol they use to stand for a generic parent. So this could be any number of carbons back here, and the OH just attached to it. Now, the names of the alcohols, very simple. They all end in OL, like alcohol. So, for instance, a 2-carbon compound that has an OH, a hydroxyl group attached to it, is called ethanol. Again, based on 2 carbons, OL at the end tells me it's an alcohol. If it was 1 carbon, it would be methanol. That's wood alcohol. Okay, so you can see we've got methanol, ethanol, propanol, butanol. By the time you get to like 3 carbons, you got to say, well, where's the OH group? So there's like 1 propanol. That means the OH group is attached to the number 1 carbon. Or 2 propanol, where it's attached to the 2nd carbon. As a matter of fact, that brings up something that I mentioned earlier. What if I did put that OH group in the middle of 3 carbons? This would be called 2-propanol, but it has a common name. It's called isopropyl alcohol. Remember the term isopropyl, I used it before when I said, what if we attached a 3-carbon branch to a parent chain but grabbed it by the middle carbon? They call that an isopropyl group. Well, commonly this alcohol can be referred to as isopropyl alcohol. Technically, according to the Iupac rules though, this is its real name, 2-propanol. All right, so again, alcohols are kind of an important player, and so they show up early in the game in organic chemistry. Well, let me show you the next one. I'm kind of showing you the oxidation series here. Alcohols, if you let them sit open too long, can actually oxidize into something called an aldehyde. Let me show you that one. Okay, aldehydes all typically have this carbonyl group. That's what it's called, a C with a double bonded O. And it's always at the very last carbon on the chain, so it's always a C double bonded O capped off with a hydrogen, no more carbons south of that. All right, so if it's always on the number 1 carbon, then we usually don't have to say where that carbonyl group is in the molecule, because to be an aldehyde, it has to be right there on number 1. So for instance, if you've got a 3-carbon chain and that last carbon's got that carbonyl group on it, it's now classified as an aldehyde. Now it turns out that all the sugars or a lot of the sugars are aldehydes, and so most of the important biochemical ones are. And so this is why they introduce this kind of early, because in biochemistry, naturally, they're going to talk about sugars and all the carbohydrates, and most of those are aldehydes. All right, well, this one's named propanal. Notice the suffix now changes to an AL. So butanal, ethanal, again, you see these pop up in organic chemistry very early. Now, one other cousin of the aldehyde that I've got to show you, and I may as well do it while we're right here on the board, is called the ketone. Now, the reason they're kind of cousins is that it also has the carbonyl group, but now it's not allowed to be on the number 1 carbon. It has to be in the middle of the chain. So I'm going to put like another parent chain on the other side. Now, I put a prime there because the number of carbons doesn't have to be symmetric. It just has to be buried somewhere inside the chain and not on the end carbons to classify as a ketone. All right, so in that case, for instance, what if I put a CH3 and a C with a double bond O and then a CH3? Well, this one with 3 carbons is based on the name propane, because, or PROP, that prefix. But since it's a ketone, they refer to this one as propanone. O-N-E. So you can understand then, in this case, if we get to like 4 carbons, butanone, or 5 carbons, pentanone, we have to be careful, because when there's choices of now where the double bonded O could be, since now it's not on the ends, it's somewhere in the middle, we have to indicate by number where that carbonyl is. So you'll see things like 3-hexanone, which tells you that it's a 6-carbon ketone, but the double bonded O is on the 3rd carbon. All right, so again, you can see the Iupac system running to the rescue there. All right, well, it turns out that the alcohols, like I said, can oxidize. and they become aldehydes and ketones. Let me show you that mechanism here since we're kind of on the topic. Okay, in the oxidation of alcohols, in order to make aldehydes and ketones, this oxidation follows the same mechanism that you'll see often in organic chemistry. An oxidizing agent, for instance, something like that potassium permanganate, I may have mentioned it, it's that purple stuff we made the lake purple with. It has a tendency to steal hydrogens away from a hydrocarbon in order to oxidize it. You can almost look at it as if the oxidizing agent is going to steal two hydrogens so that it could sort of make a water molecule out of it. All right, so it's going to steal those two hydrogens from the hydrocarbon. And when it steals them from an alcohol, it steals a particular two. It steals the one from the hydroxyl group and one from the carbon adjacent to it. Apparently, those are the two easiest to pop off of there. Well, when that happens, that leaves this carbon looking for another bond and the oxygen looking for another bond. If this hydrogen disappears and one of those disappears, we end up with a carbon with a double bonded O. And since that OH was on the very last carbon of this chain, then that double bonded O occurred on the last carbon of the chain, and suddenly it became an aldehyde. So it turns out whenever an alcohol has the OH on the end of the chain, then if we leave it open too long, regardless of how many carbons are back here, it could be one propanol, one ethanol, one butanol, as long as it's one, the hydroxyl's on the end carbon, then it's going to end up making its corresponding aldehyde. In this case, ethanol became ethanal. Now it turns out, and I've told this to people before, that when you open a bottle of wine, if you leave it open, it's going to begin to oxidize. So even though it may take a while for the concentration of this to build up, it will build up. And it's this compound that causes a constriction of the capillaries in your brain, that causes the blood pressure in your head to go up. But it takes your body, for instance, if you drink some alcohol, it takes your body several hours to convert the ethanol into ethanal. But it will. And when you wake up in the morning, you may not feel very well because of this molecule. So this is the hangover molecule that your body produces from the ethanol. But if you open a bottle of wine to let it breathe for a while, I think all you're doing is creating more of those and making the hangover too soon. It's, you're not going to wait 8 hours. You're just going to have your hangover right now. So my philosophy is, if you open a bottle of wine, chug it down, before this has a chance to take hold. Well, anyway, one other thing about the oxidation here. What if the hydroxyl group was not on the end carbon? What if it was, say, in the middle? Like if I had isopropyl alcohol with the OH smack in the middle. Well, it turns out, sure enough, if you oxidize that with an oxidizing agent, essentially it's going to do the same thing. It's going to steal this hydrogen and the one on the carbon adjacent to it. Now you created a molecule where the carbonyl group is in the middle of the chain. All right, well, in that case, you created a ketone. So it turns out that when the hydroxyl group on the alcohol is on the end, then you make an aldehyde. By the way, they call those primary alcohols. When the OH group, the alcohol group, though, is in the middle of a chain, they call it a secondary alcohol. All right, so primary alcohols will oxidize to aldehydes. Secondary alcohols oxidize into ketones. So there's an interesting sequence of events that happens with organic compounds. The alcohols will oxidize into the aldehydes and ketones. Well, it turns out that the aldehydes have an interesting chemistry because they'll oxidize one more step into our next class of compounds. Okay, well, the aldehydes, turns out when they oxidize, can form this next class of compounds called the carboxylic acids. You'll notice it's got a carbonyl group and a hydroxyl group both attached to the same carbon. Well, again, Iupac couldn't pass that up. A carbonyl and a hydroxyl, they called it a carboxyl. A carboxyl group. Now, this is typical of a carboxylic acid. That's what they're referred to as. Now, it's interesting that when you throw them in water, at least if the hydrocarbon chain is short enough, they'll dissolve in water and they'll split up weakly into a carboxylate anion and a 3-hydrogen ion. So they are weakly acidic. As a matter of fact, One of them is very common. Notice that this carboxylic acid is CH3 and then a C with a double bonded O and an OH. Now, this technically is referred to as ethanoic acid. This is the way that they name all of the carboxylic acids. If there were 3 carbons back here, including the carboxyl carbon, if there were 3 carbons, it would be called propanoic acid. 4 carbons, butanoic. And this always has to be on the end of the chain because it's used up all 4 of its bonds. So there isn't anything south of this. All right, but we know this by a different name. As a matter of fact, if you look at the formula, this is HC2H3O2. This is acetic acid, the acid that's in vinegar. Well, that's its common name. It turns out that its technical Iupac name is ethanoic acid, not acetic acid. But you can see that acetic acid is one of the organic carboxylic acids. All right, now I want to show you quickly how this happens from an aldehyde. Turns out that if you take an aldehyde and oxidize it, in this case, an oxygen actually gets inserted in between the carbon and the hydrogen. You have to use an oxidizing agent willing to give up an oxygen atom. Well, in that case, you end up with, sure enough, a carboxylic acid. Now, this doesn't work with ketones. It only works with the aldehydes. So you can see that primary alcohols have kind of an oxidation scheme then. A primary alcohol where the OH group is on the very end of the chain can easily be pushed another step and become the corresponding aldehyde. That aldehyde can then be pushed a little further and become its corresponding carboxylic acid. Now, one other kind of interesting cousin to the carboxylic acid is this next class of compounds called the esters. Let me put them up. Okay, well, this cousin to the carboxylic acid is the class of compounds referred to as esters. They've got this typical structure, parent chain back here, with what looks like a carboxyl group. Normally with a carboxylic acid would be a double bond O and an OH. But instead, there's other carbon atoms attached on here. And again, this doesn't have to be symmetric. The number of carbons here doesn't have to be the same number as here. Now, this makes for an interesting shape to this molecule. And consequently, all of the good fruit fragrances and a lot of the flower fragrances are ester compounds. They have a high vapor pressure, so consequently, they'll get out in a vapor state very easily. And they interact with the enzymes that are in your olfactory system that set off certain smells. For instance, if you just put 2 carbons back here and put 5 carbons up here in front, you end up with banana smell. I mean, it smells pretty darn close to bananas. Now, bananas have like 3 or 4 esters that make up their entire smell, but the main one is with the 5 carbons out here and 2 back here. It turns out if you put 1 here, no, I'm sorry, yeah, 1 back here with methyl and put 8 out here, it smells like oranges. So depending on the shape of the molecule, it sets off an entirely different set of enzymes in your nose, and suddenly you smell different fruit smells. So cherry, strawberry, these are very unique chain links, and all you have to do is change the shape of the chain that's attached behind the carboxyl group or carbonyl group and to the north of the carbonyl group, and sure enough, you'll get a different fragrance. Well, we used to do a lab. As a matter of fact, it's called the esterification reaction. Here it is. Use a carboxylic acid and use an alcohol. And the alcohol has to have this part of the R chain, and the carboxylic acid has to have this part of the R chain. You use sulfuric acid, and it draws a water molecule out of the center of that. Sulfuric acid is a great dehydrating agent. You can pull a water molecule out between 2 molecules, and it'll join them together. So it joins them together right here and forms an ester and a water molecule. All right, so this was a very easy reaction, and we would put out sets of alcohol carboxylic acid so that our students could make like pineapple smell and blueberry smell. And we had banana, we had wintergreen, which smelled really good. I always liked it when they made a big batch of wintergreen, and just the whole room smelled good. But one day, somebody decided to take the carboxylic acid from the pineapple smell and mix it with the alcohol from the blueberry smell to make blue pineapple. I don't know what they were trying to make, but they did make was essence of dead raccoon, and we had to evacuate the lab. It was just the most horrendous smell. And so we realized, I mean, the whole wing of the college just reeked. I mean, for hours of this death smell that came out of the lab. And so we had to eliminate most of the possibilities there. And so we came down to the fact that we could do wintergreen and banana. And even if they mixed those up, you couldn't make anything that smelled nearly as bad as the essence of dead raccoon. But I always thought that esters were an interesting class of compounds, and again, very easy to make. But it turns out that sure enough, in human physiology, you see a lot of this esterification. As a matter of fact, all of the fats are considered triesters of glycerol. So when you get into lipid chemistry, suddenly here are the esters. All right, well, one more class of compounds, and I promise I'll shut up. Okay, this class of compounds, the ethers. Now, they typically have this oxygen bridge in between a couple parent chains. Again, they don't have to be symmetric. This R can be a different length than this one. But the one you think of whenever anybody says ether is the one they used as an anesthetic. And now that ether was diethyl ether. So just from its name, you can kind of see what's going on here. Both side chains were both ethyl groups. Now, they don't have to be symmetric, like I said. You could have like ethyl methyl ether. They go alphabetically, by the way. And so you could come up with some nice tongue twisters for this. But you understand, it's very simple how they name the ethers. Now, again, this one, physiologically, you breathe ether fumes, you're going to sleep. I don't care who you are. It just definitely shuts down certain synapses and you're going to sleep. Now, one interesting other piece of chemistry that goes on with the ethers is this. If left open or exposed to an oxidizing agent, they'll actually oxidize into an organic peroxide. Now, these peroxides are extremely explosive just to the touch. So they have an interesting chemistry all to their own. So again, these will show up in organic because you'll see that there's some very, very interesting reactions that you can do even to manufacture ethers. Now, I showed you that one esterification reaction before where we took a water molecule out between two molecules. You can join two alcohols exactly the same way by using a dehydrating agent and steal a water molecule from the middle of those two. Well, that leaves an oxygen looking for something to bond to and an R group looking for something to bond to. That's called the Williamson ether synthesis. Okay, so again, interesting chemistry, and when you get to organic chemistry, you're going to see that reaction. All right, one more. Okay, amines. It turns out amines are all based on nitrogen. They're all actually based on ammonia. NH3 has this Lewis structure. But if we rip off one of its little hydrogens and replace it with some carbon atoms, for instance, like we put this, a methyl group, this is called methylamine. All right, very tricky to name. Now, amines occur in a lot of different organic compounds. And I always joke that Lanza Chemical down here on Route 29 or 24, they manufacture amines. And they have a real fishy smell to them. As a matter of fact, what makes dead fish smell like dead fish are the amines that are in it. So I joke that Lanza makes artificial dead fish smell down there. But in essence, if you take an ammonia molecule and start substituting the hydrogens for it, you can make primary amines, secondary amines, tertiary amines, depending on how many hydrogens you substitute. You can come up with interesting names. There's trimethylamine, which would mean thered be a methyl group at each of the three hydrogens, has a lone pair on it, so that there's no bond there, just the lone pair. And then you could have, ethyl methylamine. So you can kind of mix and match and just substitute the hydrogens with alkyl groups. Now again, the amines have a very interesting chemistry that goes on with them. And when you get to human biochemistry, obviously the amino acids have an amine on one end of the molecule and a carboxylic acid on the other. Remember, I had a picture of the amino acids up here earlier. So it turns out amine chemistry is important to us, and so consequently, if you're headed down that path to organic chemistry or biochemistry, you're definitely going to see these guys. Okay, well, like I said, I wish we had more time to talk. I'm just getting used to this. We could cover a lot of ground this way. But I'm afraid we're running out of time. And so this organic chemistry is just going to have to wrap it up. Now, the take-home exam that I gave you has questions that extend out into those other chapters. And again, I tried to pick and choose some salient topics for you to dig around in at least. I know you're buried in homework out there, so I tried to make it easy to find those answers for the take-home exam. Now we're going to have another Zoom meeting before the final just to go over that last exam. So we'll have plenty of contact between now and then. But if you have any questions or problems, again, please don't hesitate to contact me. And I'll see you at one of the Zoom meetings. So long.